Nearly 1,000 years ago, a star in the constellation Taurus exploded its light reaching Earth in the year 1054. What remains is the Crab Pulsar, a neutron star spinning faster than the blades of a jet engine, flashing beams of energy across space. In this video, we'll explore how such an object was born from a supernova. If you enjoy it, please like, subscribe, and share, and tell us in the comments, do you think pulsars are cosmic lighthouses or something even stranger? Thank you for watching. Now, let's begin. In the depths of the constellation Taurus, a vast cloud of matter drifts outward in all directions. It is the remnant of a star that ended its life in a brilliant outburst recorded on Earth in the 11th century. Now, nearly 1,000 years later, the debris has formed what astronomers call the Crab Nebula, an intricate structure of filaments and haze that continues to spread into the surrounding interstellar medium. The outward expansion is measured with careful instruments showing that the material races away at thousands of kilometers per second, a motion that has not ceased since the day of the explosion. Though the human eye with a telescope might perceive a delicate glowing cloud, the reality is one of immense momentum and silent force. The outer regions of the nebula mark the boundary where the shock front from the ancient detonation still moves ahead, pushing against gas and dust that once lay undisturbed between the stars. The outer shell appears faint but structured, dotted with strands of glowing hydrogen and heavier elements carried outward from the core of the collapsed star. These filaments twist and curl as they extend into space, shaped by turbulence left from the blast. Some appear as long, thin threads, others as knots or loops, each revealing the different densities and velocities present in the expanding shell. Careful measurements over decades allow astronomers to compare images and see that these features do not stand still. They drift steadily, marking the persistent outward growth of the nebula. Observations in visible light capture the reddish hues of hydrogen and the greenish glow of oxygen, but other instruments record emission at wavelengths the eye cannot detect. Radio maps show broad arcs of low-frequency radiation, while X-ray telescopes display sharper outlines, where the gas is still heated to millions of degrees. Each wavelength uncovers a layer of the same outward surge, building a composite picture of the shell that spreads far beyond the central star. The expansion does not proceed into emptiness alone. It meets the tenuous material that already exists between the stars, what scientists call the interstellar medium. At the edge where the nebula's front encounters this material, faint shock structures appear. These represent regions where gas is compressed and heated by the encounter, forming an ever-thinning boundary between the remnant and the galaxy beyond. The surrounding space is not uniform, so the shell expands more quickly in some directions and more slowly in others, producing the slightly irregular outline visible in images. The Crab Nebula thus shows the interaction of an ancient explosion with the medium of the Milky Way, a collision that continues to sculpt both nebula and surroundings. This process carries on silently far beyond the scales of human lifetimes. The material that now forms the outer regions once lay deep inside the original star. It contains hydrogen and helium from outer layers, but also heavier elements forged in the nuclear furnaces of stellar evolution. As the shock wave passed outward, it carried these atoms into interstellar space, seeding the galaxy with ingredients that will one day become part of new stars and planets. What is seen today in the Crab Nebula's shell is both a snapshot of destruction and a source of future creation. The outward speeds remain astonishing. Even after centuries of deceleration from contact with surrounding gas, the filaments still race at thousands of kilometers per second. At such velocities in the span of a human lifetime, the material crosses distances comparable to the entire solar system. Yet from Earth, nearly 7,000 light-years away, the expansion is subtle. Astronomers must use precise instruments to measure changes in the nebula's size over decades, revealing the constant growth that would otherwise remain imperceptible. This expansion carries with it a record of the supernova that once lit the sky. The brightness seen by observers in China, Japan, and the Middle East in the year 1054 marked the birth of this remnant. Now the faint shell holds the echoes of that event stretched into a glowing cloud. The Crab Pulsar, though central and hidden deeper within, owes its existence to the same event. The neutron star sits at the heart, but its influence reaches outward, powering radiation and structures within the nebula. At this outermost region, however, the processes are those of inertia and collision, the straightforward momentum of ejected matter carrying on its path. The expansion has slowed somewhat compared to its earliest days, but the shell will continue to enlarge for tens of thousands of years before it fades into the broader background of interstellar gas. The shapes seen in the outer shell are more than mere visual ornaments. They encode the physics of how the explosion occurred. Slight asymmetries hint that the star did not explode evenly in all directions. Variations in density show where layers of the original star were thicker or thinner. Chemical composition varies from strand to strand, reflecting the layered structure of the progenitor. Oxygen-rich filaments trace deeper layers, while hydrogen-rich arcs belong to the surface regions of the former star. These details frozen in motion let scientists reconstruct the story of a single stellar death. Over time, the light from these filaments diminishes as they spread and thin. Yet they remain luminous because the central pulsar drives a wind of energetic particles and radiation that illuminates the nebula from within. Without that continuous input, the outer shell would have faded more quickly. In this way, the expansion is not a passive structure alone, but part of a larger system sustained by the central object. Still at the edge, the forces are weaker, and the outermost regions glow faintly compared to the inner haze. When telescopes focus on this faint rim, they capture the frontier where matter from one star collides with the wider galaxy. This frontier is thin and changing a faint arc across the sky, yet it holds the entire history of the event within its expansion. To those who study it, the outer shell of the Crab Nebula is both a relic and a laboratory. It demonstrates how supernova remnants evolve, how shockwaves propagate, and how elements are spread through space. It also frames the more dynamic processes inside. The boundary defines the space within which the pulsar and its wind create complex structures. The shell is the canvas upon which the central energy paints its patterns. As the centuries pass, the shell will continue to grow, becoming more diffuse and merging with the medium around it. But for now, nearly a millennium after the star's death, the expanding remnant remains clearly visible, a testament to a single event that reshaped its environment. Observing the shell is like seeing the outermost ripple of a stone cast into water, a ripple that continues to travel outward long after the impact. The Crab Pulsar lies at the center, but here in the outer regions one sees first the legacy of the explosion itself, the enduring flight of matter away from its source, carrying with it both the memory of violence and the seeds of future formation. Inside the outward shell, the eye is drawn to countless filaments that lace the nebula with intricate forms. These are not smooth clouds, but finely structured threads, some stretched into long arcs, others curled into knots and loops. Together they form a web that extends across the face of the remnant, delicate in appearance, yet composed of material hurled outward at extreme speeds centuries ago. The filaments shine because they contain atoms excited by shock waves and radiation releasing energy as visible light. Through telescopes, they create a scene of thin glowing strands crossing a softer background haze. The arrangement is not random. Patterns of density and turbulence govern their shapes, sculpted by the physics of gas under pressure. The expanding shock front did not sweep outward evenly. It left behind zones of compression, where gas bunched into strands and voids where material thinned. Over time, these differences elongated, producing the lattice now visible. Some filaments appear bright and sharp, suggesting denser collections of matter, while others are faint, indicating lower concentrations. The knots embedded in the filaments are small clumps of heavier material, perhaps once part of deeper layers in the original star. Their persistence shows how resistant dense cores of gas can be holding their integrity, even as they travel outward for centuries. Modern imaging reveals these features in extraordinary detail. High-resolution cameras mounted on space telescopes capture every twist and turn, allowing comparisons with earlier photographs to show that the filaments drift with the overall expansion. By aligning images from different decades, astronomers track their slow migration outward. Each strand moves away from the central region, yet retains its identity like frozen waves traveling across a sea of light. The speeds measured match the known age of the supernova, confirming that they are debris from the event recorded in the year 1054. The web of filaments tells a story of turbulence. As the gas expanded, instabilities arose where different layers of matter collided. These instabilities caused fingers of dense material to push into lighter surroundings, producing the branching forms now seen. Similar processes occur in many astrophysical settings, but the Crab Nebula displays them with rare clarity. The contrast between filaments and background provides a natural laboratory for studying fluid dynamics on scales far beyond anything on Earth. When examined through different filters, the filaments reveal their varied compositions. Some glow strongly in hydrogen, the most abundant element of the original star's outer layers. Others shine in oxygen or sulfur marking zones from deeper regions of the progenitor. These variations are not simply cosmetic. They provide direct evidence of the internal layering of the original massive star. During its lifetime, the star built heavier elements through nuclear fusion, depositing them in successive shells. The explosion tore these layers apart and scattered them, but the distinction remains visible in the filaments. Each strand carries a signature of its origin inside the star. Spectroscopy. The technique of dispersing light into its component colors makes these signatures precise. When the filaments are studied this way, sharp emission lines appear at characteristic wavelengths. These lines identify the presence of oxygen, sulfur, nitrogen, and other elements. They also reveal the conditions within the filaments, such as temperature and density. The data show that the filaments are often a few thousand degrees Celsius hot enough to radiate visible light, yet cool compared to the million-degree gas that surrounds them. This temperature difference creates striking contrasts in the nebula's appearance, with thin, bright strands superimposed on a diffuse background glow. The arrangement of filaments also provides insight into the geometry of the original explosion. Their distribution is not perfectly spherical. In some regions they cluster more densely, while in others they thin out. This asymmetry suggests that the star did not collapse uniformly, but released its energy more strongly along certain directions. The debris field records those variations, a permanent imprint of the final moments of the progenitor star. The Crab Pulsar at the center adds further complexity by driving energetic winds that interact with the filaments. Close to the pulsar, moving features such as wisps and arcs are visible, but even at greater distances the wind exerts pressure on the filaments, shaping their forms. Some strands appear bent or twisted where they encounter this outflow, evidence of an ongoing dialogue between the expanding debris and the central engine. This interplay keeps the nebula active, preventing it from becoming a static remnant. Over centuries, the filaments will continue to move outward, but their brightness depends on continuous energy input from within. Without the pulsar's illumination, many of the strands would have faded. The neutron star's radiation keeps atoms in the filaments excited, ensuring that they remain visible across the spectrum. Thus, the filaments are not isolated relics, but participants in a larger system glowing as long as the central pulsar continues to energize the nebula. The delicate appearance of the web belies its scale. Each filament stretches across distances measured in light years. A single strand could encompass the span of the solar system many times over. Yet from Earth, nearly 7,000 light-years away, they appear as fine threads crossing the face of the nebula. Their sheer size underscores the magnitude of the original explosion, which expelled enough material to create structures of this scale. The Crab Nebula remains one of the most detailed and well-studied examples of such filamentary structure. Other remnants show similar webs, but few are as close or as bright, allowing such fine resolution. This makes it a cornerstone for understanding how supernova debris evolves. Scientists compare its filaments to those in other nebulae to test theories of shock, physics, turbulence, and chemical mixing. Each observation adds to the picture of how stars end and how their material disperses into the galaxy. The human eye drawn to images of the Crab Nebula often notices the filaments first, for they provide sharp definition against the background haze. They give the remnant its distinctive texture like threads of a vast cosmic tapestry. Yet beyond aesthetics, they embody the physics of expansion, turbulence, and chemical diversity. They represent the physical record of a star's life and death, stretched into space as a luminous web. The Crab Pulsar lies hidden deeper inside, powering the glow, but here in the filamentary web one sees the immediate aftermath of the explosion frozen in motion and carried outward through centuries. The nebula continues to change slowly and imperceptibly to casual viewing, but persistently over time. The filaments lengthen their reach, drift farther from the center, and interact with the medium beyond. They show that the aftermath of a supernova is not a single event, but a process unfolding across ages. At this stage, nearly a millennium after the explosion, the filaments remain bright and distinct, bearing witness to the extraordinary forces that created them. Their presence defines the character of the nebula's outer structure and frames the more dynamic processes within. The delicate web formed from the heart of a destroyed star expands, still marking both an end and a beginning in the cycle of matter in the Milky Way. Within the glowing filaments of the Crab Nebula lies a deeper record of the star that once existed, expressed most clearly through the chemical traces that the explosion left behind. Each strand and knot is a reservoir of elements forged in nuclear reactions during the star's lifetime and during the explosion itself. By studying the spectrum of light from these regions, astronomers uncover the fingerprints of different atoms, allowing them to reconstruct the story of how the star lived and died. Among the most prominent elements revealed are oxygen, hydrogen, and sulfur. Each radiates at specific wavelengths, producing distinct colors when observed through filters. The greenish-blue glow, often seen in photographs, corresponds to oxygen, while hydrogen produces red hues and sulfur emits in deeper crimson. Together, these emissions paint the filaments with a multicolored appearance, though most of the radiation lies outside the visible range detectable only with specialized instruments. These variations are not cosmetic, but carry information about the star's layered structure. During its life, the progenitor star built heavier elements in successive shells, with hydrogen fusing into helium in outer layers, helium burning into carbon and oxygen in deeper zones, and more advanced reactions generating still heavier nuclei. When the star exploded, these layers were blasted outward and intermixed. The Crab Nebula preserves this distribution with filaments containing different proportions of elements depending on which region of the progenitor they originated from. This chemical diversity demonstrates that the nebula is more than a luminous cloud. It is a dispersed archive of stellar evolution. The process of identifying these elements relies on spectroscopy, in which light is spread into a rainbow and examined for narrow features known as emission lines. Each line corresponds to a transition in an atom or ion, acting as a precise signature. When astronomers study the Crab Nebula in this way, they detect strong lines from oxygen, sulfur, nitrogen, and hydrogen, among others. The brightness of these lines indicates how abundant each element is in different filaments, while their width and shift reveal temperatures, densities, and velocities. This information confirms that the filaments are hot enough to radiate visibly, but cooler than the surrounding medium, typically a few thousand degrees Celsius, compared to the millions of degrees found in the interior haze. In addition to visible light, the nebula radiates in ultraviolet, infrared, and X-rays, each wavelength, uncovering further detail about chemical composition. Infrared observations reveal cooler dust grains, intermixed with the gas remnants of material that condensed during and after the explosion. These grains consist of carbon and silicates, the same basic ingredients that later form planets and solid bodies. The presence of dust alongside glowing gas shows that the supernova did not only scatter atoms, but also contributed to the complex mix of solid particles in interstellar space. The Crab Nebula is thus a source of both raw gas and condensed material for future star-forming regions. The chemical traces also provide evidence of nuclear processes that occurred during the explosion itself. When the star collapsed, the sudden compression and rebound generated a flood of neutrinos and shock energy that transformed some nuclei into new elements. These freshly synthesized atoms now reside in the nebula. Measurements of isotopes in the gas, when possible, offer a glimpse into those moments of extreme physics. Although direct detection of short-lived isotopes is rare, the abundances of stable elements hint at the explosive nucleosynthesis that accompanied the birth of the Crab Pulsar. Another striking aspect is how the distribution of elements maps the geometry of the explosion. Certain filaments rich in oxygen extend in particular directions, while hydrogen-dominated filaments stretch in others. This anisotropy shows that the blast was not perfectly spherical, but directed energy unevenly. The chemical traces make these differences visible, as if the nebula carries a fossilized image of the explosion's asymmetry. The outer regions where the nebula meets the interstellar medium are enriched with lighter elements, while deeper filaments closer to the center show heavier nuclei. Such patterns provide crucial evidence for models of how massive stars end their lives. Over time, the expansion of the nebula thins these chemical reservoirs. The density of atoms decreases as the filaments spread and their brightness diminishes. Yet the Crab Pulsar sustains their glow by bathing the nebula in high-energy radiation and particle winds which excite atoms and cause them to continue emitting light. This input ensures that the spectral signatures remain visible centuries after the explosion, enabling ongoing study. Without the central source, many of the chemical traces would fade into invisibility. The Crab Nebula is often compared with other remnants to understand how typical its composition is. In many respects, it resembles others, showing strong oxygen and sulfur lines, but it is unique in being young, close and bright enough for detailed mapping. Its chemical distribution can be studied filament by filament, providing resolution unmatched in more distant remnants. This makes it a benchmark for theories of chemical enrichment in the galaxy. The importance of this lies not only in reconstructing the star's past, but also in understanding how the galaxy gains its diversity of elements. Every atom of oxygen in a human breath, every atom of iron in blood, and every atom of calcium in bones originated in stars and supernovae. The Crab Nebula is a direct witness of that process still unfolding. The filaments are visible proof of stellar alchemy carrying the ingredients of future systems outward into space. Dust grains formed in the explosion may travel for millions of years before contributing to new planetary surfaces. In this sense, the chemical traces observed today are both an endpoint and a beginning. The detailed study of these emissions also reveals the physical conditions of the filaments themselves. Their densities, often around 1,000 particles per cubic centimetre, are high compared to the surrounding medium, but extraordinarily thin by terrestrial standards. Their temperatures measured at thousands of degrees maintain the excitation of atoms, but are too cool for further fusion. The filaments are stable structures, yet they continue to evolve as the shock waves and pulsar wind interact with them. Over decades of observation, changes in brightness and shape have been recorded, showing that the chemical traces are not static, but dynamic features within a living remnant. At the same time, the Crab Pulsar at the core provides a reference for these studies. By anchoring the distribution of elements to the central neutron star astronomers map how material from different depths of the progenitor was ejected in different directions. This mapping connects the outer shell and filamentary web back to the central object, tying together the story of collapse, explosion, and ongoing energy release. The Crab Pulsar itself remains a small but powerful presence sustaining the nebula and ensuring that its chemical traces remain visible to distant observers. The story carried in the filaments is one of continuity. Matter that once resided in the hot interior of a massive star now drifts through interstellar space, glowing faintly as it goes. In time, the atoms of oxygen, carbon, and nitrogen will mix into the galaxy and may form part of new systems. The Crab Nebula provides a snapshot of that process, frozen in an intermediate stage where the material is neither fully dispersed nor wholly confined. Its chemical traces make this process visible, reminding us that the elements of the universe are always in motion, always recycled from one structure to another. Here within the filaments illuminated by the pulsar's energy, the legacy of stellar fusion is carried outward, a record etched in spectral lines that remain detectable even after centuries. The Crab Pulsar is the compact heart, but the elements spread in its surroundings give the nebula its substance, its colour, and its enduring role in the cycle of matter in the Milky Way. At the edge of the Crab Nebula, where the expanding debris meets the wider interstellar medium, lies a zone of subtle but important interaction. Here the outward-moving shock front collides with the thin gas already present between the stars, creating boundaries that continue to shift nearly a millennium after the original supernova. Although this outer frontier is faint compared to the bright inner haze, it holds essential clues to how supernova remnants evolve and how they shape their surroundings. The interstellar medium itself is far from empty. It contains tenuous clouds of hydrogen, traces of helium, and small amounts of heavier elements spread at densities of only a few atoms per cubic centimetre. As the shock wave from the supernova ploughs into this material, it compresses and heats it, raising temperatures to millions of degrees. The result is a region of X-ray emission invisible to the human eye, but revealed by orbiting telescopes sensitive to high-energy light. In optical images, the frontier can appear as a faint arc, yet instruments tuned to different wavelengths show the complexity of the boundary, where two very different regimes of matter collide. The Crab Pulsar at the center provides constant energy that drives the expansion, but at the edges, inertia still carries the debris outward at thousands of kilometers per second. As the blast wave encounters the interstellar medium, it slows slightly, transferring energy to the surrounding gas. This energy input stirs turbulence and creates small-scale shocks that ripple through the frontier. Such interactions are crucial for understanding how elements from the exploded star eventually mix with the galaxy. Without them, the material would remain confined. Instead, the collision with interstellar gas spreads and dilutes the debris, dispersing oxygen, carbon, and other atoms across vast regions. The physics of shock interaction governs not only the Crab Nebula, but also countless other remnants. Yet the Crab offers a close and detailed example, allowing astronomers to measure how far the shock has advanced and how much energy it still carries. Over centuries of observation expansion measurements show that the outer edge moves at thousands of kilometers per second, consistent with a remnant just under 1,000 years old. The shock front does not form a perfect sphere. Instead, it shows variations in brightness and structure, reflecting both the irregular density of the interstellar medium and the asymmetry of the original explosion. In some directions, the shock meets denser clouds and slows more rapidly, producing sharper boundaries. In others, it expands into lower density regions and stretches farther, leaving a more diffuse edge. The result is a slightly elongated shell rather than a perfect circle. By mapping these differences, scientists learn not only about the supernova itself, but also about the medium into which it expands. The boundary zone is also a site of particle acceleration. As charged particles encounter the shock, they are scattered back and forth by magnetic irregularities, gaining energy with each pass. This process, known as diffusive shock acceleration, is believed to be one of the main mechanisms for creating cosmic rays, high-energy particles that stream through the galaxy. Evidence from the Crab Nebula suggests that such acceleration is indeed taking place at its outer edge. Radio and X-ray observations detect emissions consistent with particles boosted to near light speed. Thus, the faint boundary around the nebula is not only a marker of expansion, but also a laboratory of extreme physics, where ordinary gas is transformed into cosmic rays that may eventually travel far beyond the remnant itself. The presence of these accelerated particles ties the Crab Nebula to a broader galactic context. Cosmic rays from many supernova remnants fill the Milky Way, influencing the chemistry of interstellar clouds and even affecting the conditions for star formation. The Crab is a single example, but one of the best studied, showing how the interaction of a shock with the interstellar medium contributes to processes on scales much larger than the remnant itself. The outer edge also demonstrates how energy is distributed across different forms. Some remains in the bulk motion of expanding gas, some is converted to heat, some to radiation, and some to the acceleration of particles. This partitioning evolves over time, gradually shifting as the remnant expands and slows. At the current age of the Crab Nebula, much of the energy is still in motion, but a growing fraction has been deposited into the interstellar medium, heating it and stirring turbulence that will persist long after the remnant fades. Observationally, the boundary region is challenging to study because of its faintness, yet with sensitive detectors, astronomers trace faint emissions that reveal the shock structure. Narrowband imaging highlights specific atoms excited at the edge, while X-ray data shows the hot gas just behind the shock. By combining these observations, a picture emerges of a frontier that is neither static nor uniform but alive with ongoing interaction. The Crab Pulsar's influence extends even here, though diminished compared to the inner nebula. Its radiation and particle outflow illuminate the filaments near the boundary, keeping them visible. Without this internal power source, the outer edge would appear far dimmer. In this sense, the frontier is both a product of the initial explosion and sustained by the central neutron star that remains. Over the coming millennia, the shock front will continue to move outward, gradually slowing as it transfers more energy to the interstellar medium. Eventually the expansion will stall, and the material will blend with its surroundings, leaving only a faint trace of enrichment. At that distant future stage, the Crab Nebula will no longer be distinct, but its elements will persist as part of the galaxy. For now, however, the boundary remains visible, a thin shell enclosing the brighter interior. Its structure defines the scale of the remnant, marking the maximum reach of the explosion nearly 1,000 years after the event. Every observation of the Crab Nebula must account for this outer shell, for it is the stage upon which the internal dynamics play out. The frontier is both a limit and a connection. A limit because it defines the current extent of the nebula, and a connection because it links the supernova remnant to the broader interstellar medium. Beyond it lies the galaxy at large, while within it the pulsar and its wind-sculpt complex forms. The balance between outward expansion and surrounding resistance shapes the appearance of the nebula at every level. In quiet images, the boundary may appear as nothing more than a faint glow, yet it embodies immense energies and complex processes, all proceeding steadily in the vacuum of space. It shows how a single star's death can influence the environment far beyond its original size, spreading elements, stirring turbulence and accelerating particles. The Crab Pulsar is the hidden core, but here at the frontier the legacy of the explosion continues to unfold in silence. The boundary zone reminds us that supernova remnants are not static monuments, but evolving systems still in motion centuries after their birth. The Crab Nebula illustrates this with unmatched clarity, presenting a laboratory where shock physics, chemical enrichment, and cosmic ray acceleration can all be studied together. The faint shell is thus a key to understanding not only this single remnant, but also the broader role of supernovae in shaping galaxies. For nearly 1,000 years it has been expanding, changing and merging with its surroundings, and for thousands more it will continue until its matter is indistinguishable from the interstellar gas around it. Even then, the atoms carried outward will persist, part of the ongoing circulation of matter through the Milky Way, an enduring imprint of the event that gave rise to the Crab Pulsar at the heart of the nebula. Moving inward from the faint shell and filamentary web, the Crab Nebula reveals a diffuse inner glow that fills the space around the central neutron star. This haze is not produced by hot gas alone, but by a special process known as synchrotron radiation. In this phenomenon, electrons accelerated to nearly the speed of light spiral around magnetic field lines, releasing energy across a wide range of wavelengths. The result is a soft bluish glow visible in optical images, but in reality it extends from long radio waves through visible light into X-rays and gamma rays. This continuous emission, stretching over many orders of magnitude in energy, gives the Crab Nebula its distinctive brightness and makes it a cornerstone in the study of high-energy astrophysics. The synchrotron glow appears smooth when compared to the sharp filaments, yet it holds a wealth of structure. In radio images it shows broad arcs filling much of the nebula. In optical and X-ray views, finer details emerge, including rippling patterns near the pulsar. Despite these variations, the overall impression is of a steady haze, a luminous background against which the filaments are silhouetted. This glow is not static. It is constantly renewed by streams of high-energy particles flowing outward from the Crab Pulsar. Without that input, the electrons would quickly lose energy and fade. Instead, the pulsar wind replenishes them, maintaining the nebula's radiance. The central neutron star thus acts as an engine pumping energy into the surrounding cloud and sustaining its glow for centuries. The physics of synchrotron radiation arises from the fundamental interaction of charged particles with magnetic fields. When an electron moves at near light speed and encounters a magnetic field, it does not travel in a straight line. Instead, it spirals around the field line, emitting radiation tangential to its curved path. The faster the electron and the stronger the magnetic field, the more energetic the emitted radiation. In the Crab Nebula, magnetic fields shaped by the pulsar are strong enough to force electrons into tight spirals, while the particles themselves reach extraordinary energies. The combination produces radiation that spans the entire electromagnetic spectrum from radio to gamma rays. This makes the nebula one of the most luminous and widely observed objects in the sky, used as a calibration source for telescopes of many kinds. The intensity of the glow reveals the enormous energy budget of the system. The Crab Pulsar rotates about 30 times per second, and with each rotation it loses a small amount of its rotational energy. That lost energy is carried away in the pulsar wind, a stream of relativistic particles and magnetic fields. The synchrotron haze is the visible manifestation of this outflow, glowing across space as particles interact with fields and release radiation. Over the centuries, the pulsar has slowed slightly, but it remains an immense power source, capable of sustaining the nebula's brightness far into the future. Observing the synchrotron emission at different wavelengths uncovers different aspects of the process. At radio frequencies, the emission traces lower energy electrons spiraling in relatively weak fields. At optical wavelengths, it reveals intermediate energy particles. At X-ray and gamma-ray energies, it requires the highest energy electrons moving in the strongest fields near the pulsar. Each band therefore probes a different population of particles and a different region of the nebula. By comparing these observations, scientists build a layered picture of how energy flows outward from the central star. The spatial distribution of the glow also reveals important patterns. The emission is brightest near the pulsar, where particle acceleration is most intense. Moving outward, the brightness diminishes as electrons lose energy and radiation weakens. This creates a gradient of color and intensity, with the innermost regions glowing strongly in blue and violet, while the outer zones appear softer. The filaments, being cooler and denser, stand out against this background, their emission dominated by atomic lines rather than synchrotron continuum. Together, filaments and haze form a composite structure, one marking the chemical remnants of the star, the other displaying the ongoing influence of the pulsar. Another striking feature of the synchrotron glow is its polarization. Because electrons spiral in ordered magnetic fields, the emitted radiation is polarized, meaning that its electric field has a preferred orientation. By measuring this polarization, astronomers can map the direction of magnetic fields within the nebula. Observations show a complex but coherent pattern, with fields shaped by the outflow from the pulsar. These measurements confirm that magnetic structure plays a central role in shaping the appearance of the nebula and guiding the flow of energetic particles. Over time, the synchrotron glow evolves. High-energy electrons radiate away their energy rapidly on timescales of years to decades, so the brightest X-ray features change over short periods. Lower-energy electrons last longer, so radio emission remains stable over centuries. This difference creates a layered evolution. The inner high-energy glow flickers with activity, while the outer lower-energy haze persists. This dynamic range of timescales adds to the Crab Nebula's value as a laboratory for studying particle acceleration and energy loss in real time. The Crab Pulsar itself is only a few tens of kilometers in diameter, yet it energizes a nebula 6 light-years across. The synchrotron glow is the visible bridge between the two scales, linking the tiny neutron star to the vast surrounding cloud. Every photon of this diffuse emission carries information about an electron's journey, from the pulsar outward, spiraling along magnetic fields and shedding energy as light. The sheer number of such electrons is staggering enough to bathe the entire nebula in steady luminosity. The Crab Nebula's synchrotron emission is so bright and consistent that it serves as a standard candle in astronomy. Instruments across the world and in orbit calibrate their detectors by observing it. Its steady glow in X-rays, for instance, makes it a reliable reference for comparing data from different observatories. In this way, the nebula is not only an object of study but also a practical tool for science, its constancy enabling precision across multiple instruments. Yet even with its apparent steadiness, the synchrotron glow shows subtle variations. Close to the pulsar, ripples and arcs appear and shift over weeks, evidence of ongoing changes in the particle wind. These variations demonstrate that the nebula is not a static shell, but a dynamic environment constantly replenished and reshaped by the central engine. The haze we see at large scales is the integrated result of countless small processes, each electron tracing a spiral path in a magnetic field before releasing its energy into light. The importance of the synchrotron haze extends beyond the Crab Nebula. It illustrates the same physical processes that operate in distant active galaxies, pulsar, wind nebulae, and even around black holes. By studying the Crab in detail, astronomers gain insight into phenomena across the universe. The nebula serves as a nearby laboratory, where theories of particle acceleration and radiation can be tested under conditions impossible to reproduce on Earth. The Crab Pulsar, though small, is thus a cosmic engine whose effects resonate far beyond its immediate surroundings. For nearly 1,000 years, the synchrotron glow has illuminated the nebula, ensuring that the remnant of the ancient supernova remains bright. It will continue for centuries, more gradually fading, only as the pulsar slows and its output declines. Until then, the glow defines the Crab Nebula, filling its interior with a steady radiance that complements the sharper filaments at the edge. In the quiet depths of space, this diffuse light marks the presence of one of the most energetic processes known, an enduring beacon powered by the rotation and magnetism of the Crab Pulsar at the heart of the remnant. Closer to the pulsar, the smooth haze of synchrotron radiation gives way to features that shift on timescales humans can observe. These are the wisps, delicate arcs of brightness that form near the boundary, where the pulsar wind meets the nebular interior. They appear as curved ripples aligned roughly in concentric patterns around the central star, brightening and fading, advancing outward before dissolving into the background glow. Unlike the ancient filaments of the outer nebula, which move slowly over centuries, the wisps change within weeks or months. This restless motion makes them among the most dynamic elements of the remnant, a vivid reminder that the Crab Nebula is still very much alive. The wisps mark the termination shock of the pulsar wind. The neutron star at the core pours out a stream of charged particles at nearly the speed of light, carrying with it magnetic fields. When this wind slams into the slower moving material of the nebula, it cannot continue freely. Instead, it decelerates abruptly, forming a shock front. At this frontier, particles are compressed and accelerated, releasing radiation that appears as bright arcs. These arcs are the wisps constantly renewed by the pulsar's outflow. As new waves of particles are injected, fresh wisps form closer to the star and then move outward, replacing those that fade into the haze. Observations with high-resolution telescopes capture this cycle, showing new features appearing and drifting outward at thousands of kilometers per second. Each wisp represents a snapshot of interaction between the pulsar wind and the surrounding nebula, visible only because of the synchrotron light produced by energized electrons. The appearance of the wisps changes across wavelengths. In radio images, they are faint and diffuse, while in optical views they appear as bright, rippling arcs. In X-rays, they are sharper, still tracing the highest energy particles. The consistency of their shape across different bands confirms that they are a fundamental feature of the Wind Nebula interaction, not an artifact of a single observing method. This multi-wavelength view allows astronomers to study how particles of different energies respond to the same conditions, deepening the understanding of acceleration processes at relativistic shocks. The movement of the wisps demonstrates the scale of energy involved. To sustain features that shift so quickly across light-years of space requires a continuous supply of relativistic particles. The Crab Pulsar provides this energy through its rotation, which converts rotational kinetic energy into the particle wind. With each second, the star loses a tiny fraction of its spin, and that lost energy powers the entire nebula. The wisps are one of the clearest visual expressions of this ongoing transfer, transforming invisible streams of particles into visible arcs of light. Their behavior underscores the link between the pulsar's slowing rotation and the nebula's evolving appearance. The geometry of the wisps suggests that they are shaped not only by the shock, but also by the pulsar's magnetic field. The arcs align roughly perpendicular to the pulsar's spin axis, forming a pattern that echoes the equatorial plane of the neutron star. This alignment indicates that the pulsar wind is not uniform in all directions but concentrated in certain zones. The result is a structured interaction with wisps forming preferentially where the outflow is strongest. The arcs can be thought of as glowing markers of the regions where energy flow is channeled outward most effectively. Over decades of monitoring, astronomers have seen wisps appear, shift, and fade repeatedly. Their persistence as a phenomenon, despite individual features coming and going, shows that the interaction between pulsar wind and nebula is steady. The detailed shapes may change, but the underlying process continues without interruption. This steadiness provides an opportunity to study the dynamics of shocks under extreme conditions, where particles move at near light speed and magnetic fields are extraordinarily strong. Few natural laboratories offer such access, making the Crab Nebula unique. The wisps also interact with nearby structures such as knots of emission close to the pulsar. These compact bright regions lie slightly offset from the star and remain more stable than the shifting arcs. Together with the wisps, they form part of the inner nebula, a zone of constant activity shaped by the pulsar's energy. The combination of steady knots and moving wisps reveals different aspects of the same wind, some tied to persistent outflows, others to transient fluctuations. The contrast adds richness to the picture of how a neutron star powers its surroundings. Studying the wisps requires instruments of high sensitivity and resolution. The Hubble Space Telescope and the Chandra X-ray Observatory have provided some of the most detailed views, capturing sequences of images over months and years. These time-lapse observations show the wisps drifting outward, almost like waves rippling across water, though on a scale of light years and driven by relativistic particles. Such visual evidence is rare in astrophysics, where most processes evolve over millennia. The Crab Nebula is one of the few places where change is fast enough to watch unfold within a human lifetime. The Crab Pulsar remains the central engine, but its influence is most apparent in the restless motion of the wisps. Without the pulsar's constant outflow, the nebula would be fading steadily, its energy slowly dissipating. Instead, the pulsar sustains a cycle of renewal, injecting fresh energy that produces arcs of light repeatedly. This connection between a compact neutron star only a few tens of kilometers wide and a nebula 6 light-years across is striking. It illustrates how the energy of a single object can dominate an entire region of space, reshaping it continuously. The wisps also serve as a testing ground for theories of plasma physics. In laboratories on Earth, it is impossible to reproduce conditions where particles are accelerated to near light speed and magnetic fields shape flows on scales of light years. Yet by studying the brightness, speed and variability of the wisps, scientists gain insight into processes that occur in environments ranging from pulsar wind nebulae to jets from black holes. The Crab Nebula thus provides a bridge between theory and observation, grounding abstract physics in visible structures. Though the wisps seem delicate, they are signatures of extreme violence at microscopic scales. Each electron that contributes to their glow carries energy millions of times greater than that of particles in terrestrial accelerators. The collective result of countless such particles is the smooth arcs visible across space. The quiet arcs seen in images are the surface expression of turbulent processes far beyond human experience. Over centuries to come, the wisps will continue to form and fade, marking the persistent presence of the pulsar wind. They will gradually change as the pulsar slows and its energy output decreases, but for now they remain active, a vivid sign that the Crab Nebula is not a fossil, but a living remnant. The outer filaments show the aftermath of the explosion. The synchrotron haze reveals the continuous input of energy, but it is in the wisps that change can be seen directly unfolding in near real time. Their ceaseless motion draws the eye to the heart of the nebula, where the Crab Pulsar continues its silent rotation, powering a spectacle of light that shifts and flows through the cosmic haze. Closer still to the pulsar, beyond the shifting arcs of the wisps, distinct structures emerge that take on more definite forms. These are the knots and the torus features that mark the organized geometry of the nebula's inner regions. Unlike the delicate and transient wisps, the knots appear as compact bright spots, while the torus presents itself as a ring-like structure encircling the pulsar's equatorial zone. Together they reveal how the pulsar wind, shaped by rotation and magnetic fields, imposes order upon the surrounding chaos. The torus is the most striking of these features. It appears as a flattened ring oriented around the neutron star's spin axis, slightly tilted as seen from Earth. In optical and X-ray images, it glows brightly with arcs and layers that suggest stratification of emission. This toroidal shape arises from the concentration of the pulsar wind in the equatorial plane. Instead of flowing evenly in all directions, much of the wind is channeled outward along this belt, producing a circular distribution of energy and particles. The result is a luminous ring that expands outward its brightness, marking the regions where energetic particles spiral in magnetic fields and radiate synchrotron light. The torus is not uniform. It shows bright patches, arcs and filaments within its circumference, evidence of turbulence and instabilities. These variations shift slowly, revealing that the torus, though more stable than the wisps, is still a dynamic structure. High-energy observations in X-rays show that the torus is brightest close to the pulsar, where the energy of the wind is greatest and fades outward as electrons lose momentum. Optical and radio observations reveal similar patterns, though with less sharpness, reflecting the longer-lived lower-energy electrons in those bands. Embedded within or near the torus are knots, compact clumps of emission that stand out from the surrounding glow. Some are located very close to the pulsar offset, slightly from its position, while others appear along the arcs of the torus itself. These knots are brighter and more localized than the diffuse emission, suggesting concentrated regions of particle acceleration or compression. They may mark sites where magnetic fields converge or where the pulsar wind encounters obstacles in the surrounding nebula. Observations over decades show that while some knots persist, others fluctuate in brightness or shift slightly, indicating ongoing activity. The combination of torus and knots provides evidence for the structured nature of the pulsar wind. Instead of a chaotic outflow, the wind is shaped by the pulsar's strong magnetic field and rapid rotation. The result is an organized pattern of energy release with equatorial outflows producing the torus, and more compact features arising from localized interactions. This geometry matches theoretical models that predict anisotropic winds from rotating magnetized neutron stars where energy is directed preferentially along the equator and poles. The Crab Pulsar, by virtue of its rapid 30 rotation per second spin and intense magnetic field, exemplifies these dynamics. The torus is more than a visual curiosity. It is a diagnostic of the pulsar's energy output and wind structure. By measuring its size, brightness and spectrum, astronomers estimate how much energy the pulsar deposits into the nebula and how that energy is distributed. The torus acts as a visible marker of where the wind transitions from free expansion to interaction with the nebular medium. It is the inner stage upon which the pulsar's influence is written most clearly. The symmetry of the torus also allows astronomers to deduce the orientation of the pulsar's spin axis. From Earth, the tilt of the ring reveals the angle at which we view the system. This geometric information is essential for interpreting the pulsar's pulsed radiation and aligning it with the structures of the nebula. The connection between spin orientation and nebular morphology demonstrates how a single compact object governs the appearance of a structure 6 light-years wide. The knots add further layers of complexity. Their brightness often rivals that of the pulsar itself, though they are far less compact. The innermost knot, located just a fraction of a light-year from the neutron star, has been studied intensely as it provides direct evidence of where the pulsar wind interacts most strongly with its environment. The knot's persistence suggests that it is anchored by a stable feature in the wind or magnetic field, yet it also shows fluctuations hinting at variability in the pulsar's outflow. Other knots farther out appear and fade, perhaps as turbulence in the torus concentrates energy temporarily. The combination of steady and variable features underscores the dynamic equilibrium maintained in the nebula's core. High-resolution X-ray images show that the torus is accompanied by arcs that mirror its curvature, giving the impression of nested rings. These arcs are interpreted as shock structures formed where the pulsar wind slows abruptly and releases energy. The nested appearance suggests that the interaction occurs over multiple layers, with each arc marking a different stage in the deceleration of the wind. The overall effect is a complex but coherent system where geometry, magnetism, and particle dynamics intertwine. The Crab Pulsar at the center provides the energy, but the torus and knots reveal how that energy is distributed and manifested. The torus also demonstrates polarization like the synchrotron haze. Measurements show that its light is highly polarized with orientations tracing the magnetic fields within. This polarization maps the structure of the fields that guide the pulsar wind, confirming that magnetism is central to shaping the torus. The degree of polarization also provides clues about the uniformity of the fields, with higher polarization indicating more ordered structures. Thus, the torus is not only an image but a magnetic fingerprint. Compared to the fleeting wisps, the torus changes more slowly, evolving over years rather than weeks. This stability provides a framework within which the more transient features arise. The torus is the backbone of the inner nebula, defining the equatorial plane and sustaining emission across the spectrum. The Crab Pulsar's equatorial outflow maintains it, ensuring that the ring continues to glow as long as the pulsar spins rapidly. The knots punctuate this structure with concentrated brightness, highlighting localized phenomena that may represent the extremes of particle acceleration. Together they form a system that bridges the small scale of the pulsar with the large scale of the nebula. In observing these features, scientists gain insight into how pulsar winds operate, how shocks form, and how energy is partitioned between different regions. The Crab Nebula serves as a natural laboratory for these studies, its proximity and brightness allowing detail that would be impossible in more distant systems. The torus and knots stand as testimony to the power of a neutron star carving order into the expanding chaos of supernova debris. They remind us that the Crab Nebula is not only an aftermath, but an ongoing interaction sustained by the heartbeat of the pulsar within. While the outer filaments carry the chemical story of the progenitor star, the torus and knots reveal the physics of the pulsar's present activity. They are the structures where theory meets observation, where the invisible processes of magnetism and relativistic winds become visible in arcs and clumps of light. The Crab Pulsar is the core, but through the torus and knots, its influence is written clearly into the nebula, shaping its form and sustaining its glow across the centuries. From the equatorial torus, the eye is drawn outward along two thin, straight beams of emission that stretch in opposite directions. These are the jet's narrow channels of energy that extend from the Crab Pulsar's poles and cut through the surrounding nebula with remarkable precision. In high-energy images, they appear as faint but distinct streaks emerging directly from the pulsar's position and maintaining their orientation over vast distances. Unlike the broad, circular glow of the torus, the jets are focused and linear, marking a different aspect of how the pulsar distributes its energy into space. The formation of these jets is tied to the pulsar's magnetic field and rapid rotation. As the neutron star spins 30 times per second, its intense magnetic field channels outflows along the poles. The result is a pair of oppositely directed streams of relativistic particles that pierce the nebula. These polar beams carry significant energy, though less than the equatorial outflow that powers the torus. They nonetheless demonstrate the anisotropy of the pulsar wind, with energy emerging not uniformly, but preferentially along specific directions set by the geometry of the magnetic and rotational axes. Observations show that the jets are not static. They flicker, bend, and sometimes appear to twist, indicating that the flow of particles is turbulent and subject to instabilities. At times, bright knots appear along their length, then fade as the flow moves outward. These knots may represent shocks where the jet encounters denser regions of nebular material, compressing particles and producing enhanced synchrotron radiation. Despite these fluctuations, the overall structure of the jets persists, aligned consistently with the pulsar's poles. The alignment of the jets provides crucial information about the orientation of the neutron star. Combined with the torus, which lies along the equatorial plane, the jets confirm the spin axis of the pulsar. This three-dimensional geometry mapped from Earth through careful observation reveals how the central star shapes its environment in a coordinated pattern. The torus marks the equator, while the jets mark the poles together, forming a system that reflects the pulsar's internal dynamics on scales millions of times larger than its own size. The jets are particularly prominent in X-ray images where the highest energy electrons emit strongly. They appear as straight luminous channels extending for light years. In optical images they are fainter, barely perceptible against the brighter haze of the nebula. Radio observations capture them less clearly as the lower energy electrons radiate less efficiently in the narrow channels. This wavelength dependence emphasizes that the jets are sites of extreme particle acceleration, producing emissions dominated by the highest energies. The variability of the jets has been documented over decades. Long-term monitoring shows that they bend and shift slightly over time, as if buffeted by unseen currents in the nebula. At times, the base of a jet brightens suddenly, suggesting a surge of energy from the pulsar. These changes occur over months to years, much slower than the rapidly moving wisps, but faster than the centuries-long drift of outer filaments. The Crab Nebula thus offers dynamic phenomena on multiple timescales, from weeks to millennia, all tied to the pulsar's influence. The existence of the jets connects the Crab Pulsar to other astrophysical systems where collimated outflows occur. In distant galaxies, supermassive black holes launch jets that stretch for thousands of light years. Though the scales are vastly different, the underlying physics of magnetized rotating objects channeling energy into narrow beams is similar. By studying the Crab's jets, astronomers gain insight into processes that govern objects across the universe. The Crab Pulsar provides a nearby and accessible laboratory for understanding how magnetic fields can focus relativistic flows into coherent streams. The jets also demonstrate the role of magnetic reconnection, where field lines break and rejoin, releasing bursts of energy. Instabilities in the pulsar's magnetosphere can trigger such events, leading to sudden enhancements in the jet's brightness. These episodes highlight the complex interplay between steady rotation and chaotic magnetic processes. The Crab Nebula is one of the few remnants where such details can be resolved, allowing theories of plasma physics to be tested against direct observation. While the torus dominates the equatorial region with its broad glow, the jets extend as delicate but powerful features. Their presence balances the nebula's appearance, adding linear elements that contrast with the circular structures. Together they form a symmetrical system with energy flowing outward in complementary directions. The Crab Pulsar, though tiny, projects its influence along axes that define the geometry of a structure 6 light-years wide. This order emerges from the apparent chaos of the supernova remnant, an imprint of rotation and magnetism written across space. At the tips of the jets, where they fade into the diffuse nebula, their energy merges with the surrounding glow. The boundaries are not sharp as the relativistic particles disperse and mix with the broader synchrotron haze, yet their influence extends far, injecting high-energy particles into the outer regions and contributing to the overall luminosity of the nebula. The jets thus serve as conduits, delivering energy from the pulsar to distances where it would not otherwise reach directly. Detailed study of the jets has also revealed polarization consistent with ordered magnetic fields along their length. This confirms that they are not random flows but guided streams shaped by coherent structures. The degree of polarization combined with spectral measurements constrains the strength and orientation of magnetic fields within the jets. Such data provide valuable tests for theoretical models of pulsar wind nebulae and the role of magnetism in shaping astrophysical outflows. The Crab Pulsar's jets also highlight the efficiency with which a neutron star can convert rotational energy into directed flows. Each second, the pulsar loses energy as it spins down. A fraction of that energy emerges in the form of jets, a focused output that carries particles and magnetic fields away from the star. Over centuries, this process has sustained the narrow beams visible today, testimony to the enduring power of the pulsar engine. The jets, like the torus and wisps, are visible only because of synchrotron radiation from relativistic electrons. Their light is thus indirect, a byproduct of particles spiraling in fields. Yet this indirect glow reveals the otherwise invisible processes at work near the pulsar. By tracing the jets across the nebula, astronomers follow the path of energy from the star to the surrounding space. The Crab Nebula becomes not only a relic of an ancient explosion, but a dynamic system where energy continues to flow outward in structured ways. Over future millennia, the jets will weaken as the pulsar slows and its output declines. For now, they remain prominent, their straight lines extending like signposts from the central star. They join the filaments, the haze, the wisps, and the torus, in forming a complete picture of the Crab Nebula, a system both complex and coherent. Each feature marks a different expression of the pulsar's energy, from broad diffuse glow to sharp linear streams. The jets in particular underscore the focused nature of that energy, the ability of a neutron star to channel power along magnetic axes with remarkable precision. The Crab Pulsar is the compact core, but the jets carry its influence far outward, carving narrow beams of light through the surrounding haze. Their presence enriches the portrait of the nebula, showing that even within apparent disorder, there exists a framework set by the physics of rotation and magnetism, persisting across centuries and distances measured in light years. At the heart of the nebula lies the neutron star itself, known as the Crab Pulsar, a compact object only about 20 kilometers in diameter, yet weighing more than the Sun. This tiny sphere of matter is the source of the nebula's continuous power, and one of its most remarkable qualities is its pulsed emission. As the star rotates roughly 30 times every second, beams of radiation sweep across space like the light from a cosmic beacon. Whenever one of these beams crosses Earth's line of sight, telescopes detect a pulse, a sharp burst of energy arriving with clock-like precision. This phenomenon defines the pulsar, distinguishing it from other neutron stars that may not beam in Earth's direction. The pulses are observed across the electromagnetic spectrum. In radio frequencies, the pulsar was among the earliest to be detected, with its steady rhythm confirming its identity. In optical light, it appears as a faint star that brightens and dims 30 times each second, a feat visible even with small ground-based telescopes under precise observation. In X-rays and gamma rays, space-based instruments reveal pulses that are sharper and more intense, marking the extremes of particle acceleration near the star. The alignment of these pulses across wavelengths demonstrates the consistency of the underlying mechanism, even though different regions of the pulsar's magnetosphere contribute to different energies. The timing of the pulses is so regular that the Crab Pulsar is often compared to an atomic clock in its stability, though small irregularities called glitches occasionally occur. These glitches represent sudden changes in rotation speed thought to arise from internal rearrangements of the neutron star's superdense matter. Aside from these rare events, the star maintains its rhythm with remarkable fidelity, allowing scientists to track its slowing over decades. Each rotation loses a fraction of energy, transferred into the pulsar wind that powers the nebula. The very act of pulsing is thus a byproduct of the star's rotational energy, expressed in beams of radiation directed by its strong magnetic field. The geometry of these beams arises from the misalignment of the magnetic and rotational axes. If the magnetic poles were aligned perfectly with the spin axis, the radiation would remain fixed, but because they are tilted, the beams sweep around as the star spins. This sweeping motion ensures that the pulses are detectable whenever the beam crosses Earth. The double-peaked pulse profile of the Crab indicates that both poles contribute beams visible from our vantage point. Each rotation thus produces two main bursts of emission, recorded consistently across frequencies. The Crab Pulsar's rapid spin is a consequence of conservation of angular momentum during the supernova collapse. The progenitor star, many times larger than the Sun, rotated slowly during its life. When its core collapsed into a neutron star, its radius shrank to only tens of kilometers. Like a spinning ice skater pulling in their arms, the star's rotation rate increased dramatically, producing the 30 rotation per second speed observed today. Over centuries, the pulsar has slowed slightly, but the reduction is minimal, leaving it still one of the fastest known among young neutron stars. The pulsed emission has been studied extensively since its discovery in the late 1960s. Continuous monitoring has allowed astronomers to measure the gradual slowing of the rotation and to model the loss of energy. These measurements confirm that the pulsar is a young object only about 1,000 years old, consistent with the historical supernova of 1054. The Crab Pulsar is thus one of the rare cases where an astronomical object can be directly linked to a recorded event in human history. The pulses also vary in subtle ways across wavelengths. In radio, the emission is thought to arise from regions higher in the magnetosphere where particles are accelerated along field lines. In optical and X-rays, the emission comes from closer to the surface, where magnetic fields are stronger. In gamma rays, the pulses originate from still more extreme conditions, possibly near the light cylinder, the distance where field lines cannot co-rotate with the star. Each frequency thus probes a different layer of the pulsar's environment, yet the overall timing remains locked to the rotation. This multi-wavelength consistency provides one of the clearest pictures of how a pulsar radiates. Another important aspect of the pulsed emission is its polarization. Measurements show that the light is polarized in ways that trace the orientation of the magnetic field. As the star rotates, the polarization angle sweeps, providing a map of the magnetic geometry. This information helps to constrain models of the magnetosphere where charged particles are guided by intense fields far stronger than anything producible on Earth. The Crab Pulsar's polarization data remain among the most detailed for any pulsar, confirming the role of magnetism in shaping the beams. The precision of the pulses allows them to be used as tools for other studies. For instance, by measuring the arrival times of pulses across different wavelengths, astronomers test theories of relativity and probe the interstellar medium between the Crab and Earth. Small delays in pulse arrival reveal how free electrons in space disperse the signal. This makes the pulsar a probe not only of its own physics, but also of the material it traverses on its way to Earth. The Crab Pulsar is also notable for producing giant pulses, occasional bursts much brighter than normal. These giant pulses occur unpredictably, lasting only microseconds, but release enormous amounts of energy. Their origin remains a topic of study, possibly linked to coherent emission processes in the magnetosphere. Whatever the mechanism, their presence adds to the Crab's reputation as one of the most remarkable pulsars known. The pulsed emission anchors the entire nebula. Without the constant injection of energy, the synchrotron glow would fade and the filaments would dim. Each rotation of the pulsar feeds the system with fresh energy, expressed not only in the broad wind but also in the beams that sweep across space. The regular flashes visible to Earth are a direct line to the heart of the process, an observable signature of the central engine. For nearly 1,000 years, the Crab Pulsar has spun ceaselessly, broadcasting its rhythm across the galaxy. It will continue for millennia, more gradually slowing but maintaining its pulsed emission, as long as its rotation and magnetism persist. The Crab Pulsar thus stands as both a relic of an ancient explosion and a living source of energy, its pulses connecting the history of the supernova with the ongoing dynamics of the nebula. Each flash is a reminder that at the center of the delicate filaments and diffuse glow lies a neutron star of extraordinary density and power, rotating in silence yet announcing its presence with unwavering regularity. The pulsed beams of radiation that sweep across space are only part of the story. Surrounding the Crab Pulsar is a region where charged particles are accelerated to extraordinary energies, producing light that spans from radio to gamma rays. This is the acceleration zone, an invisible yet immensely powerful domain, in which the rotational energy of the neutron star is converted into the motion of electrons and positrons, moving at nearly the speed of light. It is within this region that the conditions exist for one of the most efficient particle accelerators in the known universe, far surpassing anything humans can construct on Earth. The origin of the acceleration lies in the combination of rapid rotation and intense magnetism. The Crab Pulsar's magnetic field is billions of times stronger than Earth's, and sweeps around 30 times each second as the star spins, This rotation of such a powerful field induces electric fields strong enough to rip charged particles from the surface and hurl them outward. Once free, the particles are guided along magnetic field lines where they gain energy, continuously spiraling through space in tightly wound paths. The result is a stream of relativistic electrons and positrons that form the pulsar wind feeding the nebula and producing the synchrotron glow. In this acceleration zone, particles achieve energies sufficient to emit gamma rays, the most energetic form of light. Observations from space-based telescopes sensitive to high-energy radiation have revealed that the Crab Pulsar is one of the brightest gamma-ray sources in the sky, producing photons with energies up to trillions of electron volts. These emissions are evidence of processes at the extreme edge of known physics, where particles are pushed to speeds so close to light that relativistic effects dominate their behavior. The gamma rays detected as pulses aligned with the pulsar's rotation show that the acceleration zone is tightly linked to the star's magnetosphere. The structure of this zone is complex, shaped by the interaction of magnetic and electric fields. Some models suggest that acceleration occurs near the magnetic poles, where particles stream outward in beams that create the observed radio and optical pulses. Others indicate that acceleration takes place farther out near the so-called light cylinder, the distance from the star where magnetic field lines can no longer co-rotate with the neutron star. At this boundary, fields stretch and reconnect, releasing bursts of energy that drive particles to extreme speeds. The Crab Pulsar is unique in that it emits across the spectrum with unusual brightness, making it a touchstone for testing these models. In addition to synchrotron radiation, another process called curvature radiation plays a role. As charged particles follow the curved paths of magnetic field lines, they emit high-energy photons, particularly in gamma rays. This mechanism helps explain the sharp pulses observed at those energies. Meanwhile, inverse Compton scattering may also occur where relativistic electrons collide with the lower-energy photons, boosting them to higher energies. These processes combine to create the multi-wavelength emission that makes the Crab Nebula visible from radio to gamma rays, all ultimately rooted in the acceleration zone surrounding the pulsar. The scale of the energies involved is difficult to comprehend. A single electron in the acceleration zone may carry as much energy as a grain of sand dropped from a tall building on Earth, an astonishing concentration of power in a single particle. Multiplied by the vast number of particles in the pulsar wind, the total energy output sustains the entire nebula. This demonstrates the efficiency of the Crab Pulsar in converting rotational energy into particle acceleration, a process that has persisted since the star's birth nearly 1,000 years ago. Observational evidence for the acceleration zone comes not only from gamma-ray pulses, but also from rapid variability in the nebula itself. Occasionally, the Crab has produced sudden flares in gamma rays, increasing in brightness by factors of several within hours. These flares reveal that localized regions of acceleration can release energy explosively far faster than expected. Though rare, such events show that the acceleration zone is not steady alone, but also capable of sudden intense activity. These flares highlight the dynamic nature of the magnetosphere and the ongoing interplay between magnetic fields and charged particles. The Crab Pulsar's acceleration zone is also a key site for the production of positrons, the antimatter counterparts of electrons. The strong fields can create pairs of electrons and positrons from the vacuum through processes involving gamma rays and intense magnetic fields. These pairs feed the pulsar wind, increasing its density and ensuring a continuous supply of charged particles. The Crab Nebula is thus not only a source of high-energy photons, but also of antimatter particles, demonstrating the breadth of physics occurring in this compact environment. Polarization measurements of the pulsed emission provide further insight into the acceleration zone. The alignment and rotation of polarization angles across the pulse profile reflect the geometry of the fields where the emission originates. The data show that the fields are highly structured, consistent with models of ordered magnetospheres. Yet the variability of polarization during flares suggests that the fields can also rearrange, suddenly reinforcing the picture of a dynamic and unstable environment. For decades, the Crab Pulsar has served as a calibration point for gamma-ray telescopes because of its brightness and consistency. Its pulses provide a benchmark against which other high-energy sources are measured. Yet at the same time, the Crab continues to surprise with flares and anomalies, reminding scientists that the acceleration zone is not fully understood. It remains a frontier of astrophysics, where familiar laws of electromagnetism operate under conditions far beyond terrestrial experience. The significance of this acceleration extends beyond the Crab itself. Processes similar to those in its magnetosphere are thought to occur in the environments of black holes, magnetars, and even in the jets of active galaxies. By studying the Crab, astronomers refine models that apply across cosmic scales. The neutron star is small, but the physics it demonstrates has universal reach. Every pulse of gamma rays, every flare, every wisp illuminated by accelerated electrons contributes to the broader understanding of how nature pushes particles to the highest energies. The Crab Pulsar continues to spin, and with each rotation its acceleration zone drives particles outward, sustaining the nebula and producing light visible across the universe. This hidden region, though invisible to the naked eye, is the true powerhouse of the Crab Nebula, where rotational energy is transformed into radiation and motion on scales that defy human comprehension. The Crab Nebula is famous for its filaments, wisps, torus, and jets, but all of these are secondary expressions of the energy born in the acceleration zone. It is here, close to the pulsar, that the fundamental processes occur, linking the small scale of a neutron star to the vast scale of a light-year-wide nebula. The acceleration zone is thus both a mystery and a key, a compact region where the universe reveals its capacity for extreme sustained for centuries by the rotation of a star that died but left behind a beacon of enduring power. The environment around the Crab Pulsar is shaped above all by its magnetosphere, the region where the star's intense magnetic field dominates the motion of charged particles. This magnetosphere extends far beyond the physical surface of the neutron star, reaching to the boundary where field lines can no longer keep pace with the rapid 30 rotation per second spin. Within this domain, particles are guided, accelerated, and trapped by field lines billions of times stronger than any magnetic field found on Earth. The magnetosphere is where the rotational energy of the pulsar is converted into radiation and particle flows, producing the emissions that make the star visible across the spectrum. At the core of this structure lies a dipolar magnetic field, similar in geometry to that of a bar magnet but vastly stronger. The field lines emerge from one magnetic pole, arc through space, and return to the opposite pole. Because the magnetic axis is tilted relative to the rotation axis, these lines sweep around as the pulsar spins. Near the star, the field is so strong that it dictates every movement of electrons and positrons, locking them into tight spirals and forcing them to follow curved paths. The energy stored in this field is enormous enough to drive continuous radiation and particle acceleration for thousands of years. The magnetosphere is divided into different zones, each with its own dynamics. Near the surface, closed field lines loop back to the star-trapping particles in tight arcs. Farther out, open field lines stretch outward indefinitely, allowing particles to escape into the pulsar wind. The boundary between these regions, known as the polar cap, is a key site for particle acceleration. charged particles pulled from the surface stream outward along the open field lines, emitting radiation as they go. These flows are thought to be responsible for the pulsar's radio emission produced through coherent processes at high altitudes above the surface. Another important region is the so-called outer gap, located farther from the star near the light cylinder, the distance at which field lines can no longer co-rotate with the neutron star. In this region, strong electric fields arise as magnetic structures stretch and reconnect, producing bursts of acceleration. It is here that high-energy gamma rays are thought to originate, generated by electrons and positrons traveling at near-light speeds and radiating as they curve along field lines. The Crab Pulsar is especially luminous in gamma rays, making its outer gaps among the most efficient particle accelerators known. Observations of polarization across the pulse profile confirm that different regions of the magnetosphere contribute to different parts of the emission. The sweeping angle of polarization during each pulse traces the rotation of magnetic field lines, providing a kind of map of the magnetosphere's structure. By analyzing these changes, astronomers reconstruct how the beams of radiation are shaped and where within the magnetosphere they arise. For the Crab Pulsar, the evidence points to a complex interplay between polar cap and outer gap regions, with both contributing to the multi-wavelength emission. The magnetosphere is not static. It evolves as the pulsar loses rotational energy and as internal processes alter the configuration of currents and fields. Occasionally, sudden rearrangements occur, producing glitches or gamma-ray flares. These events reveal the dynamic nature of the magnetosphere, where vast amounts of energy can be released in moments. The Crab Nebula has exhibited such flares during which its gamma-ray brightness increases dramatically over hours or days, suggesting rapid reconfiguration of magnetic structures near the pulsar. These outbursts provide rare glimpses of the underlying processes that govern the magnetosphere's behavior. The scale of the magnetosphere is immense compared to the star itself. Though the neutron star is only 20 kilometers across, its magnetosphere extends thousands of kilometers outward, filling the space with structured fields. Beyond the light cylinder, where field lines open and particle wind dominates the influence of the magnetosphere, continues indirectly guiding flows that shape the torus jets and wisps. The magnetosphere is thus the origin point for all the larger-scale structures seen in the nebula. Every wisp, filament and jet owes its existence to the fields and currents generated within this compact region. The Crab Pulsar's magnetosphere is also a source of radio noise used by scientists as a probe of the interstellar medium. As the pulses travel outward, they pass through the plasma of the magnetosphere, gaining distinctive signatures in their polarization and dispersion. These signatures provide information about the density and structure of the plasma close to the pulsar. Combined with other observations, they confirm that the magnetosphere is filled with an enormous number of electron-positron pairs created through cascades initiated by the star's intense fields. Gamma rays produced in the magnetosphere collide with magnetic fields and generate new particle pairs, which in turn emit more radiation and create further pairs. This cascade process ensures a steady supply of charged particles to sustain the pulsar wind. The Crab Pulsar is unusual in that it emits strongly across the electromagnetic spectrum, making its magnetosphere accessible to study in more detail than most other pulsars. Each wavelength reveals different aspects of the same environment. Radio pulses trace coherent emission from high-altitude plasma streams. Optical pulses reveal synchrotron radiation from intermediate energies, and gamma rays expose the extremes of outer gap acceleration. Together, these data paint a picture of a magnetosphere that is both highly structured and highly dynamic. The efficiency of the Crab Pulsar's magnetosphere is extraordinary. With each rotation, it loses a small amount of rotational energy on the order of a few trillion watts. Most of this energy flows into the pulsar wind, but a fraction emerges as radiation directly from the magnetosphere. This balance ensures that the nebula remains bright, while the pulsar itself continues to pulse across wavelengths. The magnetosphere acts as the conversion mechanism, turning the mechanical rotation of the neutron star into electromagnetic power and particle acceleration. The connection between magnetosphere and nebula is visible in the way that changes near the pulsar propagate outward. Variability in the magnetosphere, such as sudden increases in particle outflow, is reflected in the behavior of wisps and knots farther away. The inner nebula thus serves as a visible extension of magnetospheric processes, providing indirect evidence of what occurs close to the neutron star. By studying both together, astronomers link small-scale magnetic physics with large-scale nebula structures. Over time, as the Crab Pulsar slows, its magnetosphere will evolve. The field will still be strong, but the energy available for acceleration and radiation will diminish. The beams of pulsed emission will weaken, and the outflow into the nebula will decline. For now, however, the Crab Pulsar remains one of the most powerful examples of magnetospheric activity in the universe, sustaining a remnant that continues to shine nearly a millennium after the original supernova. The magnetosphere is not visible to the human eye, but its effects permeate the Crab Nebula. Every pulse, every jet, every wisp of light is a direct consequence of its structure and dynamics. It is the unseen engine that underlies all the visible phenomena, demonstrating how a neutron star only a few tens of kilometers wide can shape a cloud 6 light-years across. The Crab Pulsar may appear small and faint when seen through telescopes, but its magnetosphere reveals it as one of the most energetic and influential objects in the sky. The magnetosphere of the Crab Pulsar does not end with the guiding of particles into broad outflows. It also directs them toward the surface itself, where they strike with immense energy and leave their mark as hotspots. These bright regions, located at the magnetic poles of the neutron star, are places where streams of electrons and positrons, guided by open field lines, return and impact the solid crust. The result is concentrated heating, producing localized areas that glow in X-rays far brighter than the rest of the surface. These hotspots act as footprints of the pulsar's magnetosphere, mapping where magnetic fields connect directly back to the star. Observations of these polar regions reveal compact zones of radiation that remain aligned with the pulsar's magnetic poles. As the neutron star rotates, the hotspots sweep around in space, and when they face Earth, their X-ray emission can be detected as part of the pulsed signal. This emission is different from the broad synchrotron glow of the nebula or the coherent radio pulses. It arises from the thermal radiation of matter heated directly by particle bombardment. The temperatures of the hotspots are measured in millions of degrees Celsius, high enough to emit strongly in X-rays but confined to areas only a few kilometers across. These small footprints highlight the precision with which magnetic fields channel particles onto the surface. The contrast between the hot spots and the rest of the crust is striking. The neutron star's surface overall is already hot with residual heat from its formation still radiating outward. Yet the polar regions glow more intensely, boosted by continuous energy input from magnetospheric currents. This additional heating ensures that the poles remain brighter and hotter than surrounding zones, creating a pattern that reflects the geometry of the magnetic field. The Crab Pulsar, with its tilted magnetic axis, thus displays alternating flashes of emission from each hotspot as it spins further, contributing to the complex pulse profile seen across wavelengths. The study of these polar footprints provides clues to the structure of the crust beneath them. The crust is solid, composed of densely packed nuclei, arranged in a lattice under pressures billions of times greater than those inside Earth. When relativistic particles slam into this surface, they deposit their energy within shallow depths, producing rapid heating. The crust conducts heat differently than familiar materials, so the hot spots retain their distinct boundaries rather than spreading evenly. This unusual thermal behavior reflects the exotic state of matter in the neutron star's outer layers, where density and pressure enforce properties unlike any terrestrial solid. Variability in the hotspots has been observed, with their brightness changing over time. These fluctuations likely reflect variations in the magnetospheric currents feeding them. When the particle outflow increases, more energy strikes the poles, brightening the footprints. When the outflow decreases, the emission dims. In this way, the hotspots act as a direct diagnostic of the pulsar's magnetosphere, providing visible evidence of otherwise invisible processes. Monitoring their changes allows astronomers to link surface heating to shifts in the star's broader electromagnetic activity. The polar footprints also serve as a reference point for studying pulsar glitches. When the Crab Pulsar undergoes a sudden increase in rotational speed thought to arise from internal rearrangements, changes in the hotspot emission have sometimes been recorded. These correlations suggest that the star's crust and interior are closely tied to its magnetosphere, with disturbances inside producing effects visible on the surface. The hotspots thus bridge the gap between interior physics and external radiation, offering a window into how the neutron star functions as a whole. The scale of energy deposition at the polar footprints is immense. Each second, streams of particles carrying billions of watts of power strike areas only a few kilometers wide. The result is continuous heating that outshines most other sources of X-ray radiation in the vicinity. This energy, though small compared to the pulsar's total output, is concentrated into such tiny regions that the brightness is extreme. The polar caps shine like lighthouses on the neutron star's surface, marking the points where magnetospheric energy converges most directly. The Crab Pulsar's hotspots are among the best studied because of its brightness across the spectrum. Space telescopes equipped with X-ray detectors have imaged the pulsar repeatedly, resolving the variation in emission as it rotates. These data confirm the presence of compact polar regions consistently hotter and brighter than the rest of the surface. The alignment of these zones with the magnetic poles supports the theory that they are created by returning currents. Their persistence over decades shows that the process is stable, sustained by the ongoing rotation and magnetism of the neutron star. The physics of the hotspots also reveals how the crust resists damage. Despite being bombarded continuously by streams of relativistic particles, the surface does not erode or vaporize. Instead, the extraordinary density of the crust absorbs the energy and radiates it away as thermal emission. The balance between deposition and radiation ensures that the polar footprints remain bright but stable, glowing without disintegration. This resilience highlights the remarkable properties of neutron star matter, where gravity compresses nuclei into forms that behave unlike any terrestrial solid. The study of these surface footprints extends to other neutron stars as well, but the Crab Pulsar offers the clearest example due to its youth and brightness. In older pulsars, hotspots are dimmer and more difficult to detect. In the Crab, they remain luminous, providing a direct view of where magnetospheric energy meets the star's crust. Each footprint is a signature of the pulsar's rotation, magnetism, and particle acceleration, expressed in the simplest possible form, a glowing patch of heated matter. These hotspots also contribute to the broader pulse profile. As the star spins, the polar caps rotate in and out of view, adding thermal peaks to the complex pattern of non-thermal emission from the magnetosphere. The combined result is a pulse that spans multiple wavelengths with contributions from both surface and magnetospheric sources. This complexity makes the Crab Pulsar's signal one of the richest for study, with each component tracing a different aspect of the star's physics. Over time, the hotspots will evolve. As the pulsar slows, the particle outflow will weaken, reducing the energy delivered to the poles. The footprints will cool, gradually fading along with the broader nebula emission. Yet for now, they remain vivid markers of the Crab Pulsar's continuing activity, a direct manifestation of the link between magnetosphere and surface. They remind us that even in such extreme environments, patterns of cause and effect can be traced from spinning magnetic fields to glowing patches only a few kilometers wide. The Crab Pulsar is thus not only an engine driving a nebula, but also a star with a surface that bears the marks of its own power. The footprints on its crust embody this connection, making visible the pathways by which energy travels from the magnetosphere back to the star itself. In the silent expanse of space, the hot spots glow steadily, marking the points where currents complete their circuit returning to the neutron star that launched them. They are the luminous imprints of the Crab Pulsar's magnetism, carved into its surface and sustained by its ceaseless rotation, a reminder that even the smallest regions on a neutron star carry energies beyond imagination. Beneath the glowing polar caps and the thin outer crust of the Crab Pulsar lies a layer of extraordinary matter, the crust itself. This crust, though only about a kilometer thick, holds immense significance, for it forms the rigid shell that contains the star's deeper interior. It is unlike any solid known on Earth. Composed of nuclei packed so densely that electrons have been stripped away and form a sea of degenerate particles, the crust is both immensely strong and subject to stresses far beyond those in terrestrial materials. Here gravity compresses matter until atomic structure as we know it can no longer exist, forcing nuclei into close contact within a crystalline lattice. The outermost layers of the crust consist of heavy nuclei immersed in a sea of electrons. With increasing depth, pressures rise to such extremes that neutrons begin to drip out of nuclei, forming a fluid that mixes with the solid lattice. This unique state, known as the neutron drip layer, has no counterpart in ordinary materials. It demonstrates how matter behaves under conditions of crushing density, where the balance between nuclear forces and gravity produces new phases. The crust is thought to be arranged in layers of progressively heavier nuclei, each more neutron-rich than the one above. At the very surface, iron-like nuclei dominate, but deeper down nuclei with ever larger neutron numbers appear. The pressure forces them together, creating an ordered lattice that is rigid enough to resist deformation even under intense stress. Despite its rigidity, the crust is not unchanging. The rotation of the Crab Pulsar gradually slows, altering the balance of forces inside. As the star adjusts to these changes, the crust experiences stress, sometimes breaking in sudden shifts known as starquakes. These events release energy that may contribute to glitches observed in the pulsar's rotation. Such glitches are moments when the regular pulse timing abruptly speeds up, then settles back into its gradual slowdown. The crust's ability to fracture under stress and then realign is thought to play a central role in producing these irregularities. The energy stored in the crust is immense because of its density. A teaspoon of neutron star material would outweigh mountains on Earth. This density means that even minor shifts release vast amounts of energy. Starquakes may send ripples through the magnetosphere, affecting the pulsar's emission. In the Crab Pulsar, such events have been observed as changes in rotation rate, providing indirect evidence of crustal rearrangements deep below the surface. The strength of the crust is estimated to be enormous, far exceeding that of steel or any known terrestrial material. Calculations suggest it could withstand pressures 1 billion times stronger than those that crush matter inside white dwarfs. This strength explains why the crust can hold its shape despite the immense gravity pulling inward and the intense magnetism pushing outward. Yet its very rigidity makes it prone to sudden failure, releasing pent-up energy in abrupt episodes rather than gradual adjustments. The crust is not uniform throughout its depth. As density increases toward the outer core, matter is squeezed into exotic configurations. Theoretical studies suggest that nuclei may adopt unusual shapes in these layers, forming structures nicknamed nuclear pasta because of their resemblance to sheets rods or bubbles. These configurations minimize energy under extreme compression, providing the lowest energy arrangements for matter in such conditions. Though unobservable directly, they are predicted by nuclear physics and remain one of the most intriguing aspects of neutron star crusts. The Crab Pulsar's crust thus represents a frontier of physics, bridging familiar nuclear matter with the even stranger forms expected deeper inside. Observations of the pulsar's glitches and surface emission offer indirect windows into this hidden region. Each irregularity in timing, each sudden burst or flare may carry information about the crust's properties. Theoretical models seek to match these events with predictions of crustal behavior, refining our understanding of matter under pressures that cannot be reproduced in laboratories. The crust also acts as an insulating layer for the heat of the star's interior. Residual heat from the original supernova still radiates outward, but the crust governs how quickly it escapes. Thermal conductivity within the lattice determines the star's cooling rate. In the Crab Pulsar, which is still relatively young, the crust remains hot, contributing to the X-ray emission observed from the surface. Over time, the crust will cool and harden further, but for now it continues to radiate significant thermal energy. The interplay between the crust and the magnetic field is another key factor. The magnetic field threads through the solid lattice, anchoring itself in the rigid structure. Movements of the crust can therefore affect the field, potentially altering the pulsar's emission. Conversely, stresses in the field can act back on the crust, producing fractures or rearrangements. This coupling of magnetic and solid structures creates a dynamic system where both influence the pulsar's observable behavior. The Crab Pulsar provides a unique case because its youth ensures that the crust is still evolving. Older neutron stars have crusts that have cooled and settled, but the crab's crust remains in flux, adjusting to changes in rotation and magnetism. This makes it an ideal object for studying the link between crustal physics and observable phenomena such as glitches, pulses, and flares. Each event recorded from Earth may reflect processes unfolding a kilometre below the surface, within matter so dense that a cubic centimetre outweighs mountains. In studying the Crab Pulsar's crust, astronomers and physicists explore not only the star itself but also the fundamental laws of matter. The crust embodies conditions that push the boundaries of nuclear physics, testing theories in regimes inaccessible to laboratories. It stands as a natural experiment ongoing since the supernova of 1054 and visible through the pulsar's emission and timing. The presence of a solid crust distinguishes neutron stars from black holes, which lack any surface at all. The crust allows interactions between interior and exterior, enabling phenomena such as hotspots, starquakes, and magnetic anchoring. Without it, the pulsar would not exhibit the same rich variety of behaviors. The Crab Pulsar's crust thus plays a central role in shaping its character as both a stellar remnant and a cosmic laboratory. As centuries pass, the crust will continue to bear the stresses of slowing rotation and shifting magnetism. It may fracture again, producing further glitches and releasing bursts of energy. It will also cool and solidify, gradually changing its properties. For now, it remains a vivid demonstration of how matter behaves under conditions beyond human experience. The crust is a kilometre-thick shell surrounding one of the densest objects in the universe, a rigid skin that holds together a star collapsed from its former self into a sphere no wider than a city. Within this hardened skin lies the outer core, where matter becomes even stranger still. But here in the crust of the Crab Pulsar we encounter the first boundary between the observable surface and the hidden depths, a layer where nuclear physics and astrophysics converge, writing their story into the steady pulses and occasional disruptions recorded on Earth. Beneath the rigid crust of the Crab Pulsar lies the outer core, a region where matter takes on states, unlike anything familiar in the universe outside neutron stars. This layer extends for several kilometers beneath the crust, filling most of the neutron star's volume. Here pressures reach levels so high that atomic nuclei no longer exist as distinct entities. Instead, neutrons, protons, and electrons are squeezed together into a dense fluid. The outer core is often described as a neutron-rich liquid, where neutrons dominate but a fraction of protons and electrons remain to balance the forces at work. This exotic fluid is stabilized by the interplay between the strong nuclear force and gravity. The density is so extreme that a cubic centimeter of core material would outweigh mountains, yet within the star it flows like a liquid. Neutrons form the bulk of the matter, but protons and electrons play a crucial role in maintaining charge balance and in producing currents that may contribute to the star's magnetic field. This composition makes the outer core not simply a uniform mass of neutrons, but a complex mixture of particles in constant motion under crushing pressure. The conditions in the outer core are inferred from theoretical models and observations of neutron star behavior. Laboratory experiments on Earth cannot reproduce such densities, so scientists rely on nuclear physics extended far beyond tested ranges. Equations of state mathematical descriptions of how matter responds to pressure and temperature are applied to predict the properties of the core. The Crab Pulsar, with its known age rotation and emission, provides constraints on these models, offering indirect evidence of the physics at work deep within. One of the most intriguing aspects of the outer core is the possibility that its matter behaves as a superfluid. A superfluid is a phase of matter in which particles move without friction, allowing currents to persist indefinitely. In the neutron-rich environment of the core, conditions are favorable for neutrons to pair up and form a superfluid. Protons in turn may form a superconducting fluid, where electrical currents can flow without resistance. If these states exist in the Crab Pulsar, they profoundly affect its dynamics, including its rotation, thermal conductivity, and magnetic behavior. Evidence for superfluidity comes from pulsar glitches, sudden changes in rotational speed observed in the Crab Pulsar and others. These glitches are thought to occur when the superfluid interior, which can rotate independently of the crust, transfers angular momentum abruptly to the outer layers. The resulting spin-up produces a measurable change in pulse timing. The regular occurrence of glitches in the Crab Pulsar supports the idea that its outer core contains superfluid components, storing and releasing angular momentum in sudden bursts. The outer core also serves as a reservoir of heat. Residual energy from the supernova collapse remains trapped within, slowly diffusing outward through the crust. The thermal properties of the outer core determine how quickly the pulsar cools. Observations of the Crab Pulsar's surface temperature combined with models of heat transport suggest that the outer core is highly conductive, allowing heat to move efficiently. If superfluidity and superconductivity are present, they would further influence thermal and magnetic properties, shaping the star's long-term evolution. The magnetic field of the Crab Pulsar, already immense at the surface, may be anchored in the outer core. Currents carried by protons and electrons in the superconducting medium could sustain the field, while interactions with the crust may lead to slow evolution of field geometry. The persistence of strong magnetism in pulsars over millions of years is thought to depend on such processes in the core. In the Crab Pulsar, still young and energetic, the field remains robust, shaping the nebula and powering its emissions. The outer core is also the region where neutrinos are produced in abundance. Neutrinos are nearly massless particles that interact only weakly with matter, allowing them to escape the star freely. In the outer core, processes such as neutron-proton interactions generate streams of neutrinos that carry away energy, contributing significantly to the cooling of the neutron star in its early centuries. Though invisible, these neutrino emissions dominate the thermal evolution of the star for thousands of years. The Crab Pulsar, less than a millennium old, may still be shedding energy primarily through this channel. Direct detection of such neutrinos from distant neutron stars is beyond current technology, but theoretical models highlight their importance. The density within the outer core approaches levels where quarks, the fundamental constituents of neutrons and protons, may begin to influence behavior. Whether quarks remain confined within nucleons or begin to appear as free particles is uncertain, and the Crab Pulsar lies at the threshold where such transitions may occur. If quark matter emerges even partially, it would alter the star's equation of state and cooling properties. While evidence remains indirect, the Crab offers an observational anchor for theories of dense matter, helping scientists test possibilities for the composition of the core. Another factor shaped by the outer core is the star's ability to sustain vibrations. Like a bell struck by a hammer, the neutron star can oscillate, with the outer core transmitting these vibrations. Such oscillations may manifest as subtle modulations in pulsar timing or as sources of gravitational waves too faint for current detectors to capture. The Crab Pulsar, with its frequent glitches and dynamic behavior, may excite such oscillations, offering another avenue of insight into its interior. The transition from crust to outer core marks a profound shift in the nature of matter. In the crust, nuclei still exist in a lattice, albeit distorted by neutron drip and high pressure. In the outer core, nuclei dissolve, leaving behind a fluid of nucleons and leptons. This fluid is bound together not by atomic structure, but by nuclear forces and gravity, forming a substance that is both alien and essential to the neutron star's stability. The outer core supports the crust above it, while transmitting the weight of the entire star inward to the deeper layers. For the Crab Pulsar, the outer core is both a stabilizing and dynamic component, storing angular momentum in its possible superfluid vortices and releasing it during glitches. It also regulates cooling and sustains the magnetic field, ensuring that the pulsar continues to emit across the spectrum. In this way, the outer core is central to the Crab's identity, hidden from view, but governing much of what is observed. Over time, as the pulsar ages and cools, the properties of the outer core will evolve. Superfluidity may become more dominant. Cooling will proceed more slowly as neutrino emission decreases, and the magnetic field may shift in structure. For now, however, the Crab Pulsar's outer core remains an active reservoir of energy and dynamics, tied to the pulsar's youth and rapid rotation. It is a place where matter exists in states beyond laboratory, reach a natural crucible for physics at the extremes. The Crab Pulsar may appear to observers as a tiny flashing star, but its outer core contains the mass of the Sun compressed into a fluid of unimaginable density. In that dense ocean, neutrons drift and flow. Protons carry currents and electrons balance charges, all under gravity so intense that no escape is possible. From this hidden interior, the visible rhythms and radiance of the pulsar ultimately arise, linking the deep physics of nuclear matter to the luminous spectacle of the nebula that surrounds it. At the deepest reaches of the Crab Pulsar lies the inner core, a domain hidden far beneath the crust and outer core where pressures and densities rise beyond anything known elsewhere in the universe. Here matter is compressed so tightly that the familiar distinction between protons and neutrons may no longer hold. Instead, particles may dissolve into their constituent quarks, or arrange themselves into phases of matter that exist only under such conditions. Though direct observation is impossible, theoretical models and indirect evidence suggest that the inner core is a place where the fundamental nature of matter is revealed at extremes. The density in this region exceeds that of an atomic nucleus by several times. At such levels, the strong nuclear force normally binding nucleons together competes with the overwhelming pressure of gravity. In the outer core, neutrons and protons exist as distinct entities within a dense fluid. In the inner core, however, the spacing between particles shrinks to the point where individual identities may blur. The result could be a sea of deconfined quarks, perhaps up-down, and strange quarks forming what some theories call strange matter. Alternatively, the matter may remain nucleonic, but adopt exotic configurations with superfluid neutrons and superconducting protons coexisting in ordered states. The Crab Pulsar's inner core therefore stands at the edge of current physics, a natural laboratory for conditions beyond experimental reach. The presence of superfluidity is almost certain given the evidence from glitches observed in the Crab Pulsar's rotation. In a superfluid, neutrons pair up and flow without viscosity, forming vortices that carry angular momentum. These vortices can pin to structures in the crust or unpin, suddenly transferring angular momentum in bursts. Such processes explain the abrupt spin-ups seen in pulsar timing. If the outer core already displays superfluid behavior, then the inner core likely does so even more strongly with vast reservoirs of angular momentum stored in its depths. The superconductivity of protons may also extend into this region, enabling electrical currents to flow without resistance and anchoring the star's intense magnetic field. These currents could sustain the Crab Pulsar's magnetism over long timescales, ensuring that its beams and nebula wind persist for millennia. Yet if quark matter exists, the behavior of the inner core could be even more exotic. A quark gluon plasma similar to that created fleetingly in particle accelerators on Earth, but stable at far higher densities, may fill the center. In this scenario, quarks are no longer confined inside protons and neutrons, but move freely in a collective state. Such matter would alter the star's equation of state, changing its mass-radius relationship and its cooling behavior. If strange quarks are present, the inner core could form strange matter, potentially the most stable form of matter under such conditions. Though unproven, these possibilities are consistent with the extreme environment expected in the Crab Pulsar's core. Cooling processes in the inner core are dominated by neutrino emission. Here particles interact in ways that generate floods of neutrinos which escape freely and carry energy into space. For a young pulsar like the Crab, this neutrino cooling may still be the dominant mechanism of energy loss. The rate at which the star cools depends sensitively on whether the core is nucleonic or contains exotic phases. Observations of surface temperatures and their evolution provide indirect clues, but uncertainties remain. The Crab Pulsar's relatively high luminosity suggests that its core may not be cooling as rapidly as some models predict, leaving open the question of its exact composition. The inner core also plays a central role in the star's stability. Its immense density resists further collapse, balancing the crushing gravity that would otherwise drive the star into a black hole. The balance depends on the pressure generated by nuclear or quark matter. If the equation of state is stiff enough, the star remains stable as a neutron star. If it is softer, collapse could occur at higher masses. The Crab Pulsar with a mass near that of the Sun sits within the stable range, but the details of its inner structure determine just how close it lies to the boundary between neutron star and black hole. Gravitational waves offer a potential window into the inner core. Vibrations or oscillations within the dense matter could produce faint ripples in space-time carrying information about the star's equation of state. While current detectors cannot capture such signals from the Crab Pulsar, future observatories may one day detect them, providing direct evidence of the core's composition. Until then, the inner core remains hidden, inferred only through its influence on observable phenomena such as rotation, cooling, and magnetic behavior. The Crab Pulsar's inner core is also thought to store vast reservoirs of energy. The superfluid vortices that permeate it hold angular momentum that can be released suddenly, driving glitches. Magnetic fields anchored in the superconducting regions may store stresses that erupt in bursts, producing flares. The stability of the entire neutron star depends on the equilibrium maintained in this central region. Any shift or reconfiguration at such depths can propagate outward, altering the pulsar's emission and the nebula's response. The scale of this hidden world is difficult to fathom. A region only a few kilometers across contains matter equal to that of the Sun, compressed into states that defy terrestrial analogy. The inner core may be featureless to the eye, a uniform sea of particles, yet within it lies complexity on the smaller scales, with quarks or nucleons arranged in collective states that define the star's behavior. It is both simple in appearance and intricate in physics, the ultimate reduction of matter under gravity's relentless pressure. In the Crab Pulsar, the inner core has persisted for nearly 1,000 years since the collapse of the progenitor star. It will endure for millions of years, more gradually cooling and evolving as the pulsar slows. Whatever its exact composition, it remains stable, locked in balance between nuclear forces and gravity. The surface pulses and nebular glow that astronomers observe are merely the outer expressions of processes rooted in this hidden depth. Every beam of radio or gamma rays, every wisp of synchrotron light, every knot in the torus and every jet of particles ultimately owes its existence to the stability of the inner core. Without its ability to withstand collapse, the Crab Pulsar would not exist. The inner core is therefore the unseen anchor of the system, invisible but indispensable. In contemplating this deepest layer, one recognizes the limits of current knowledge. The inner core of a neutron star is among the least accessible regions in astrophysics beyond direct observation, and only partially accessible through theory. The Crab Pulsar, by its youth and brightness, offers some of the best opportunities to test ideas, but many mysteries remain. Whether it contains superfluid neutrons alone or superconducting protons or exotic quark matter remains unanswered. Each possibility carries profound implications not only for the star itself, but for the fundamental laws of physics. For now, the inner core can only be described through models constrained by indirect evidence, yet its influence permeates every aspect of the Crab Pulsar and the nebula it powers. It is the heart within the heart, a compact domain where matter reaches its ultimate form, where gravity and nuclear forces balance in silence, sustaining one of the most extraordinary objects in the cosmos. The Crab Nebula, with all its filaments, wisps, torus jets and pulses, is the visible testament to that hidden core, a reminder that at the center of cosmic spectacle lies a small but unfathomable engine, still turning and still holding against collapse after nearly 1,000 years.